Hello friends, this video on S block elements part 12 is brought to you by examfear.com. No more fear from exam. Now we'll talk about the trends in the chemical properties. We'll talk about the hydrides, oxides, hydroxides, reaction with water, reaction with halogen, carbonates, sulfates, nitrides. We'll talk about solution in liquid ammonia and complex compounds, similar to what we have done for alkali metals, right? Alkaline metals are also reactive, and we'll talk about the chemical properties with these. First, we'll talk about the chemical property with air. See, the beryllium and magnesium, they are inert to oxygen. Why? Because they form oxide film on their surface. So if you see magnesium plus oxygen, it will form magnesium oxide film. And this oxide film will help magnesium to save from further attack of oxygen. Right? But if you have the powdered beryllium, where even if the oxides are formed, it won't help because it's a very powdered shape, a powdered structure, then it will react with in air to form BeO and Be3N2. We'll see the equation. So beryllium, when adds an oxygen, will give BeO, and beryllium in the nitrogen from the air, it will give Be3N2. Similar magnesium also, it will react with nitrogen in the air to form Mg3. Right? If it is powdered beryllium or powdered magnesium. Correct? Same thing, right? Magnesium is more electropositive and burns with the dazzling brilliance in the air to form Mg and Mg3. But this has to be powdered, because if it is not powdered, it will form MgO or MbEO. It's a layer, oxide layer, which will stop further reaction. Right? Calcium, strontium, barium, they are easily attacked by air to form oxides and nitrides. And they also react with water, even with cold water. So they are little reactive. Let's talk about the reaction with hydrogen. So these all those group 2 elements except beryllium, it combines with hydrogen on heating to form hydrides. So if you see, but beryllium itself, we can prepare beryllium hydride not directly by heating hydrogen, but you can prepare by the reaction of BeCl2 with LiAlH4. So you have beryllium chloride, lithium aluminum hydride, you react, you get beryllium hydride. You can indirectly prepare, but directly all the other elements react except beryllium. So the reaction is metal plus hydrogen, it gives MH2, correct? So this M can be magnesium, calcium, strontium, barium. And please note, MgS2 is covalent, and while these are ionic in nature. And note that these hydrides are very reactive in water and they produce hydrogen gas. For example, I like general formula MH2 react with water, it will form MOH2 and hydrogen. Example you can take is M can be calcium, so calcium hydride plus water will give you calcium hydroxide. You can balance these reactions. Please pay some attention here, because we have seen that MgH2 is covalent in nature, right? The question that comes to our mind is why it is covalent. So if you see BeH2 also and MgH2, both are covalent in nature. This is found experimentally because they have some different structures. A little complex to understand now, but other things, for example CaH2, SrH2, they're all ionic. And if you see, if you go down the group, what happens is the size of the atom increases, right? Beryllium, magnesium and all. So size of the atom increase. Since the size increases, its ionization energy decreases, right? Because it can lose electron easily. So they become more ionic in nature. So the ionic nature increase as you go down the group. Correct? Since the ionic nature decrease, these increase, these are covalent and these are ionic. But if you talk about BeCl2 or MgCl2, they are all ionic. But since it is hydrogen here, and hydrogen is a special case because hydrogen can either take electron or it can give electron, right? Give electron, take electron, it will become stable. Also it is small in size. So we have discussed these things a little bit in the hydride chapter, where we have discussed why beryllium hydride and magnesium hydride is covalent. But if you see from the little neutral perspective, my beryllium hydride and magnesium hydride is covalent, it is more covalent actually. It's not pure covalent, it is partial covalent, partial ionic. So it is more covalent, and if you go down the groups, the ionic character is increasing, all these other are actually ionic. Same thing we had in the first, in the alkali group also. If you see the alkali group, there we had lithium, sodium, potassium, rubidium. So if you see the lithium hydride, sodium hydride, potassium hydride, so this was covalent, and these all were ionic, right? This was covalent. Similarly here also, these two are covalent, beryllium and magnesium, others are ionic. Hope you'll remember this special exception here. This is ionic actually, but this guy is covalent. So only for hydride this is there exception. Lithium hydride is covalent, small size and high charge density. Similarly here also beryllium and magnesium, they are covalent. So I have three things to remember actually: lithium hydride, the first group, and two from second group, beryllium hydride and magnesium hydride. These are my covalent, others are my generally ionic hydrides, right? So one from group 1, two from group 2, and all tops, they are generally covalent in nature. Please remember this exception. So these hydroxides can be formed by either dissolving this metal in water, metal oxides in water actually, or you react metal with water. So in both cases you will get the metal hydroxides, either metal oxides with water or metal with water, right? And please note, all the alkali hydroxides are base except BeH2, which is beryllium hydroxide, that is amphoteric. And there are some properties of this hydroxides. As I told, all the other hydroxides are basic in nature, and the basic nature increases as we go down the group. Right? As we go down the group, if you see the size increase, the ionization energy decrease, right? So they can easily form, for example, Ca, right? Ca2 plus and OH minus. So since this is more stable, there are more OH minus ions, and it's more basic. If you go down the group, the basic nature of the solution increase. And also the water solubility also increased if you go down the group. Water solubility of hydrides. So if you go down the group, the water solubility also increases. If you see the first few, beryllium hydroxide, magnesium hydroxide, they are almost insoluble in water. But if you go down, calcium hydroxide and all, they are soluble in water. So all the alkaline earth metal combined with halogens at a little higher temperature to form halides. Right? The reaction is pretty simple. You have a metal, any metal. I mean, the metal can be any group 2 alkaline earth metal. It can be beryllium, magnesium, calcium, strontium, barium. It reacts with halogens, any halogens, fluorine, chlorine, or bromine, iodine, and it gives MX2. Correct? At a higher temperature. It's a pretty simple reaction. Now for the preparation of BeF2, we use thermal decomposition method, and for BeCl2 we use metal oxide. For example, BeO, we use carbon and chlorine to get BeCl2. And we'll discuss more about beryllium chloride here. And there is an exception here. The beryllium halides, they are covalent, but other halides are ionic. As I told, the moment you go down the group, the ionic nature increase, right? So we have seen in the earlier case, my beryllium hydride and the magnesium hydride, both are covalent. But here, in case of halides, only beryllium halide, that is beryllium chloride example, is covalent, but others are ionic. Magnesium chloride, calcium chloride, they are all ionic. It all depends on the electronegativity difference between the hydrogen, beryllium, chlorine, and those kind of stuff, right? So if you see, the beryllium halides are the only halides which are covalent in this group 2, others are all ionic, right? And since beryllium halide is covalent, they are soluble in organic solvents, right? And you see the beryllium chloride, there is a special structure in the beryllium chloride actually. So if it is in the gas phase or solid state, this is the solid state, and this is also solid state, my 3-dimensional picture, and this is the gas phase. So in gas phase is the linear monomer. This is a linear monomer, in the gas phase, and if it is in the solid state, it's chain structure. If you see, right, it's all three-dimensional. If you see, it's all three-dimensional. This is horizontal, this is vertical, this is horizontal, this is vertical. This is the shape in the gas phase, solid phase. The solid phase, it is just a linear monomer. All are in the same plane in the gas actually, but in solid, they're in different planes, right? Horizontal to vertical, and they form something like this. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.